So in this video, we're going to start a new chapter. It's the first video of chapter number 9. Okay, so it's chapter number 9 and it's called areas of parallelograms and triangles. So in this introductory video, we're going to immediately start with a very interesting proof about the area of a parallelogram. And the proof is as follows. So let's read it line by line. Parallelograms on the same base and between the same parallels are equal in area. This is the statement and we have to prove the statement. It's in fact a theorem. So first let's get rid of this. Okay. Yes, delete. Now let's read it again step by step using a highlighter. Parallelograms on the same base. Okay, what does that mean? So let us quickly draw two parallelograms. So let's say yes, so this is first parallelogram. Now, using this as the same base, can I construct another parallelogram? Obviously. So I'm going to make something like this. Okay. And another line parallel to this. Oops. Uh, yes, another line parallel to this. Okay. Let us go back. And this is that line parallel to this. Okay. And then this is my another line. So you can see I have constructed two parallelograms. This is one in the black and one in the other color. These are two parallelograms which have the same base, this base. So let's call it AB. Both of them have the same base. So again, continuing the statement, parallelograms on the same base and, now this is an important condition, and between the same parallels. Now the parallelograms that we have constructed, are they between the same parallels? No, because this is one parallel line, this is another parallel line, and these two are not between the same parallels. So these are the not two parallelograms which the proof wants us to use. So let us erase them. Okay, let's erase it completely. So we want parallelograms which are on the same base and between the same parallels are equal in area. So now let's construct a parallelogram as per this condition. So first of all, I'm going to take two parallel lines. Okay, let's say these are the two parallel lines, and here let's construct them like this. Okay, because we want two parallels between the same parallels, so I've constructed these two parallel lines first. Now let's take the first base. So let's take a small base of, okay, let's take a small base here. So let's call this point A and let's call this as point B. Okay, now first I want to draw a parallelogram using AB as a base. So this is my parallelogram, okay, between the same parallels. And now I'm going to construct another parallelogram on the same base, so same base AB, and between the same parallels, between these two parallel lines. So let's do it. So okay, so this is my another parallelogram. Oh, I forgot to use the straight lines. Okay, this is my another parallelogram between the same base and between the same parallel lines. Okay, and now let's give different names to them. So I'm going to say A, B. So the first one is A, B, C, D, and let's say the second one is A, B, and P and Q. Okay, so let's again read the statement and confirm that we are constructing the same diagrams or the same geometrical figures as the proof wants us to be. Otherwise, there will be problems while proving the statement. So reading it once again, parallelograms on the same base. So ABCD and ABPQ are on the same base AB, yes, and between the same parallels, they are between the same parallel lines, yes, are equal in area. So this is the statement and we are going to prove it. So let's move a bit here. Yes. Now let's just observe one important thing. So there is one change that we will be making in order to simplify this proof, and that change is as follows. So first of all, okay, let us erase this new parallelogram that we have constructed. So the new parallelogram will be Okay, so first of all, let's extend this line. Let's extend this line. Uh, okay, let's do one thing. Let's erase this whole thing quickly, and let's construct these two parallel lines. Okay. So this is first parallel line. This is the second parallel line. Dun, 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 dun. And then we have this as our parallelogram. Oops. Hmm. Okay. Well, it doesn't look like a parallelogram, but okay, we can extend this further. And now the other parallelogram is going to be something like this. Okay. Yes. Okay. And now let's give the names quickly. This is A. Okay. A, B, C, D, the black ones, and this is going to be P, and this is going to be Q. Okay, so once again we have two parallelograms. This is ABCD, A, B, C, D, which are on the same base AB, and between these two parallel lines. And then we have A, B, Q, P, which is also on the same base AB, and two parallel lines. These two parallel lines. Okay. In fact, let's make this like, oh sorry, let's make this like this, and let's try to erase this thing. Let me zoom in. Now it will look perfect. Okay, so now what we have to prove is that the area of both these parallelograms is equal. Now one thing you must observe, and I'm going to note it down. Point number one, or let's note it down here. Point number one, area of parallelogram ABCD, okay, is equal to now let me highlight the parallelogram. So this is A, B, C, D. Okay, this is the parallelogram. Now if you focus on this geometrical figure, it consists of two different parts, right? One is this trapezium, so I'm going to make a note of it. One is equal to trapezium, so I'm going to write trapezium ABQD, plus then we have this triangle BQC, so BQC. Okay, so area of this parallelogram ABCD is summation of area of two figures. One is this trapezium ABQD, and one is this BQC. Okay, now let us erase this highlighted thing. Yes, so and similarly, if you focus on this trapezium, sorry, this parallelogram ABQP, okay, it also consists of two figures. This is figure number one, this is figure number two. So I'm going to make a note of that. Secondly, area of parallelogram ABQP, okay, that is also equal to trapezium. So I'm going to write here trapezium ABQD, okay, is the same trapezium ABQD plus triangle APD, okay, is also trapezium plus the triangle. So now once again, let's remove this highlighted thing. Okay, and let's focus on these two statements. So if you look at these two statements, we have to prove that area of ABCD, parallelogram ABCD, is equal to area of parallelogram ABQP. Okay, but we observe that this trapezium ABQD and trapezium ABQD is common to both of them. So all we need to prove is that this triangle BQC is equal to triangle APD. Let's come back to the figure. Okay, we need to prove that triangle BQC, this triangle is equal to APD. If we are able to prove this, then we can confidently say that the area of parallelogram ABCD is equal to area of parallelogram ABQP. Okay, so now this is how we are approaching. We started with the big proof that we want to prove, and then we are concluding to a narrow steps that what is the exact thing we need to prove. So our proof has reduced to, so I'm going to write it down now here, to prove. So what is the thing that we have to prove now? To prove that triangle APD is congruent to triangle BQC. Once we prove that these two triangles are congruent, then we can say that the area of both the triangles are congruent. And once the area of these two parameters are congruent, which means same or equal, then we can clearly say this area is equal to this area. Okay. So, okay, let me just, okay. Okay, first of all, let's remove this highlighted thing because we are going to need it now. Okay, and let us try to prove that this triangle is congruent to this triangle. So what I'm going to do is make space. So let us take this down. Okay, yes. Now let's try to zoom in a bit. So okay, this thing we can move it a bit here. Yeah. So now we have to prove that this triangle is congruent to this triangle. So let's start with the observations. So if you see APD and BQC, it consists of these two parallel lines. I'm going to use a highlighter now. AP and BQ. These two are parallel to each other. Why? Because they are the opposite sides of a parallelogram. So opposite sides of parallelogram are always parallel to each other. Now with these two parallel lines, consider this as the intercept. So this line is our intercept. So let me try to draw a replica of this. So it is similar to like this. This is a parallel line. This is a parallel line. Sorry. This is a parallel line. Okay. And this is one intercept to the parallel lines. Now, if you focus on these two angles, so this angle and yes, this angle. These two angles are equal to each other. Why? Because they are corresponding angles for the transversal, which means that this angle and this angle of the triangle are equal to each other. So I'm going to make this, note down this pointer. So point number one, angle APD is equal to angle BQC. Okay, what is the reason? Corresponding angles, because they are corresponding angles of the transversal we can say PQ, of the transversal PQ. Okay, P and Q, or you can even say PC, doesn't matter, it's the same whole line. Okay, corresponding angles of the transversal PQ, and thus we prove that this angle is equal to this angle. Now once again, let's get rid of this highlighted things. Okay, now focus on the other two parallel lines which these two triangles consist of. So this parallel line, okay, and this parallel line. And now think about the transfer and think about the same line as a transversal. Okay, now once again, I'm going to draw a replica of this so that it's a bit clear. So let's erase this. Let's try to get rid of this as well. Okay, so we have to draw two parallel lines. So this is parallel, these are the two parallel lines like this. Okay, and this is my transversal. Now in this figure you can say that this angle is equal to this angle. Why? Same, because they are corresponding angles for the transversal. Similarly, this angle is equal to this angle. Why? Because these are the two parallel lines and this is my transversal. So let's quickly make a note of this second point. So point number 2 is angle PDA. So PDA, okay, is equal to angle QCB. Okay, why? Same reasoning as this. I'm going to in fact copy this line of reasoning. So copy and paste, because they are corresponding angles of the transversal PQ. Okay, the only thing is we have considered different set of parallel lines. Here we have considered these two parallel lines, and in the previous statement we considered these two as the parallel lines. Okay, so let's erase this once again. So now we have got two angles of the triangle which are equal to each other. So I'm going to even erase this so that we have more space. Okay, so in our proof, now this is our focus. We have to prove these two triangles are congruent, and in these two triangles we have two angles which are congruent to each other. So now we just need one more side in these two triangles to be congruent to each other, and then we will be using AAS test to say that both these triangles are congruent to each other. So we can clearly see in this triangle APD and BQC, we can say that side AP is equal to side BQ. Okay, in fact, I am again going to use a highlighter. Side AP is equal to side BQ. Why? Because they're opposite sides of the parallelogram, and we know that opposite sides of parallelogram are equal and parallel to each other. So that is going to be my point number 3. So I'm going to, okay, so fine, we'll just make a note here itself. So this is my point number 3 here. Point number 3, side AP is equal to side BQ. Why? What is the reason? Because they are opposite sides of a parallelogram. Parallelogram. Okay. So we have one angle, we have second angle, and we have third side. And thus, now I'm going to come to, oh, I don't have a space here. Okay. So let's come down and let's take this down again so that we have space. Okay. So now by AAS test, so thus I'm going to write here thus by angle side test of congruency, okay, we can say that triangle APD is congruent to triangle BQC. Okay, that means, and this is an important conclusion, that means, what does that mean? Area of triangle APD is equal to area of triangle BQC. This is an important point, and now this point I'm going to use a highlighter here. So area of triangle APD is equal to area of triangle BQC. In fact, let's use this highlighter. Yes, this point we are going to substitute here in this statement. So these two triangles are equal in area, and this is the same trapezium. Okay, ABQD. So, and once again we conclude thus, okay, area of parallelogram ABCD is equal to area of parallelogram ABQP. Okay, and let's go back to the statement which we wrote in the beginning. So our statement was, or theorem was, that if you draw two parallelograms, okay, using the same base, so I'll use a highlighter, using the same base and between the same two parallel lines, so these are the two parallel lines, then they will have an equal area. This was our statement to be proved, and that's what we have proved in this video.